Good morning all. Am I audible? Sound is coming clear. Okay, good. So wait for a couple of minutes. Let's start off at 10 o'clock and let's see if some more people join. We have 12 of you. I'm expecting at least 50 now. But let's see, when it strikes 10, probably some more people will join. Meanwhile, nothing much to do. Just concentrate on the session. I don't think it may take 3 hours. But let's see. We will have 3 quizzes in between, so it might take that much time. So wait for a couple of minutes. I'll come back in probably around 10, 10, 1 kind of time frame. Okay, let's get started. I think some more people will join. We are at 21 viewers. Sure, by the time we get into half an hour of this session, it would cross 50. That's my belief. Let's see. Just because it is a discontinuity in terms of the start of the marathon and the today, right? Around what 3 weeks have passed. So I think that discontinuity, as well as certain students are absent because they are at IIT KGP. The date and time might not have matched, so we might have a lesser attendance today. But this will be live and recorded in my channel, which is Code to Win, and it will be part of the playlist of the DSA series. So that will complete whatever we had pending from a DSA series standpoint, the last module, right? So of course graphs and hashing is other things that are part of the module. So if we quickly go through what we are trying to cover, we are trying to cover these things today, which is on the yellow font. So we will cover about selection, bubble and insertion. We'll just touch upon it because this is something you have already done in the past. I want to spend more time on the rest of the stuff. In fact, your questions also rarely has bubble insertion and bubble selection and insertion. Mostly very short questions come from there. Major emphasis is on quick sort, merge sort and heap sort. So we will cover those in length. Anyways, we will be covering all the questions. So at that time, some amount of bubble sort, insertion sort, selection sort, we will anyways discover. But it's no different from what you learnt in your C days in the last semester. I don't want to spend much time there. Want to spend much time through which the weightage of your questions are more. So that's on the sort. We will redo heap sort. I know we had covered heap sort as a part of our marathon series last year or last month. For that matter, last year looks too long back. So we will now try to cover all of this. We have 3 sorts to cover, which is quick, merge and heap, and we will spend 1 hour there. Typically we'll try to cover it by 45 minutes, do a quiz, and then come back to the next sort. That's how it will go. We will compare all the sorts, and a lot of questions come from the comparison perspective. A lot of short questions will come from the comparison perspective. So you need to be aware of that. And needless to say, all the questions that have come in the past 10 years, irrespective of selection, bubble, insertion, quick, merge, heap, we will cover all of that. The rest of the things, hashing and graph, which is part of module 4, we have already discussed that in the marathon session. I will position the link of that session inside the Code to Win channel in the DSA series, so that from a completeness perspective, module 4 will also be complete with those videos uploaded in the DSA playlist. That being said, I hope, I just want to make sure all of you are hearing me well, all of you are seeing the screens well. Just give me a thumbs up or okay in terms of the infrastructure, whether all infrastructure is good at your end, at my end. Okay, so I'm getting some okays here. So I'm assuming that all of you can hear me well. So we will move on with what we had to cover. Right, so quickly, if I talk about the major aspect of what we are discussing today, this particular slide and the diagram on the left actually summarizes a 35,000 feet overview of what we are trying to cover today. So what we are trying to cover today are algorithms that rely on divide and conquer. Now if you see divide and conquer, it's very simple to imagine. In the diagram, if you see, there's a problem given to you. So this problem will be something that you will be asked to solve, and then what will happen is that you will divide it into small sub problems, right? And each sub problem will have a solution, right? Each sub problem will have a solution. So you will solve the smaller problems, and then those smaller problems solution you will pass on to a combination engine, and that combination engine will combine the solutions to present the actual solution back to you. So it's very simple to imagine, and it will also be very simple to probably do. So the line that I am drawing here, this is the line of the divide phase, right? So we call it as the divide phase at the top. So we are dividing the problem. We will divide the problem. All the merge sort, heap sort, quick sort, all of them will be divided into smaller problem sets, and then we will try to conquer, that is, we will try to solve all those smaller problem sets and then aggregate them together as we go along the way. That is the crunch of saying what is a divide and conquer. It has come in terms of a question which says that explain divide and conquer. So this is the explanation of divide and conquer. Exactly what is written in the diagram. You may not need to draw a diagram. Diagram is not necessary, but you need to understand that divide means dividing the problem into smaller problems, then solutioning the smaller problems, then aggregating the solutions to get the larger solution. So those are the 3 points that you have to mention. In terms of 2 other things that we had to cover, which is table sorting and in-place sorting. These are 2 things which keep on repeating itself. It's one of the key matrices that gets asked, right? And it is common to, because it is a matrix, it is common to all the sorts. Each sort can exhibit a table sorting, yes or no. Each sort can exhibit an in-place sorting, yes or no, right? So we have to be clear of what in-place sorting and what table sorting means. Suppose you have a list like this that needs to be sorted. So this is a list, right? And this list needs to be sorted, right? What is contained in this list? There is, let's say, a key. This is, let's say, a key which is containing 5, and let's say A is a value. right? So let's say A is a value of that particular key. So 5, if it is 5, it can be A. If it is 5, it can also be C. So we can see that the key is duplicate, right? In an array, if there are duplicates, then how does the sort look after the sort? So 5A came first, 5C came last, right, in the original sequence. But when you sort it, right, if you maintain that original sequence, that is 5A will come first and 5C will come last after 5A, then it is called as stable sort, right? If you disturb the original sequence of same keys or same let's say array indexes or same array values rather, then it is an unstable sort or unstable sort, right? So remember that stable sort is only applicable for arrays which have duplicate elements. In that duplicate elements, we are saying that this duplicate element occurred before the other duplicate element. After the sort, does it also occur after the duplicate element? This particular sequence is maintained. If so, it is a stable sort. So that's what stable sort is. In-place sorting is where, let's say, in-place sorting is always considered to be associated with space complexity, right? So this is what you have to remember. In-place is not with respect to time. It is always with respect to space complexity. Now, if in order to sort, you are not using any words in terms of space, we use words. In terms of time, we use order, right? So order of time, order of words. So that way, right? So that way we are saying that the words that we are using in place of in the in-place sorting, right? Those words have no dependency on n. That is, you are actually doing a space complexity of. So if I say this is the space complexity required in terms of n, then you are actually doing this, which is order of 1, right? So you are saying that I am going to take some space, but it is not going to be dependent on n. As n decreases or increases, my space would not change. My space is independent and it goes as an order of 1. If that is the case, then you are doing in-place sorting. But if your sorting requires you to generate spaces which is proportional to n, that is, you are now doing this. You are now doing this. Then you are actually talking of either an order of n, or you might be talking of an order of, let's say, order of n log n, right? So order of n log n, or you might be talking of order of, let's say, n square, right? So you might be talking about the space being dependent on n. In that case, it is not an in-place sorting, right? So in-place sorting is order of 1. Rest everything is not in-place sorting. So I hope these two concepts are clear after this. So let's move on to the actual problem statements. We will be cognizant of the time, so we will keep on looking at our time and we will try to finish this off by the quick sort, the first part of the module, by 10:45. Let us see. The last part, heap sort, will give some breather space for us. It may not take 1 hour. So even if we spill over, it should not be an issue. Now, if I come here, then what we have is quick sort. By essence, as I said, it is a divide and conquer algorithm. So given a list or given an array, that list is actually represented in this array. So this is an array where this is the 0th pocket, 1th pocket, and so on and so forth, right? So these are your index positions of the particular array. Now, in these index positions of the array, we have different numbers. Now, what we are saying is, we will say that we will take one element as a pivot element and try to position that element at the right location after the first iteration. So this is my first iteration, right? So after the first iteration, this 25 will go to the right place. All elements to the left of 25 will be less, all elements to the right of 25 will be more. So these are the basic two things we will take. So pivot, that is the element that I am choosing. So this element is called the pivot element, right? So pivot element will be at the right place, and we will also say that left of pivot will be always less than pivot and right of pivot will be more than pivot. So these are the basic fundamental objective that we have to do, or we have to remember for quicksort. If they ask you that what are the three major things that quicksort does, these are the three things that quicksort does. It chooses a pivot. Now how do you choose a pivot? Can I choose a pivot here? Yes, you can. Can I choose a pivot here? Yes, you can. There is no hard and fast rule where you want to choose the pivot. It doesn't matter where you are choosing the pivot. All it means is that wherever you choose the pivot, if 91 is the pivot, then at the end 91 should be in the correct position. All elements to the left of 91 should be less than 91. All elements to the right of 91 should be greater than 91. That's the only requirement. You choose the pivot wherever you want. Your logic will drive the pivot. Whatever you have chosen, your logic will drive that pivot to the correct position. That's what quicksort is. Right? So let us see how it happens. So what happens is, if I have chosen this pivot here and I have taken two pointers, one a left pointer which I have moved just ahead of the pivot, and one a right pointer which I have moved, which I have kept at the end of the pivot. So basically the array now becomes only this much. The array becomes this much for me, right? So I have taken it to the lower bound of the array, and I have taken R at the upper bound of the array. Those are the 2 pointers I have taken. Now what I am going to check is that is the left pointer, wherever the left pointer is pointing, is that element less than my pivot? If it is less than my pivot, I can move forward, right? But 48 is not less than the pivot. So I will stop L. I will not have my pointer move. So this pointer that I have mentioned here, this pointer will not move because 48 is not less than 28. Likewise, if I see the right pivot, or right pointer, then the right pointer should be, what is the right part? Right part should be, I have written it here, the right part should be greater than the pivot. So the right pointer should point to elements which are greater than the pivot, then only it is allowed, so it will move forward. But 14 is in the right of the pivot, and 14 is actually not greater than 25, so it is not allowed. So stop. You cannot move the right pointer. You can only move the right pointer and allow the elements to be part of your array only if these two conditions are getting satisfied. So my left pointer stays here because 48 is not less than 25, so it stops. The right pointer which wants to move in this direction cannot move because 14 is less than 25. It has to be greater. Right side has to be greater. So unless it gets greater, it cannot move. And likewise the left pointer, unless it gets lesser, it cannot move. So when 48 and 14 are positioned wherever they are, this is how they are positioned after this particular small step or sub step is done. Then 48 and 14 are positioned here, and what happens is we will therefore swap 48 and 14, right? So when both the pointers stop, they all want to move. Like I am saying that left pointer wants to move right, right pointer wants to move left. But when they both stop, I will swap them, right? So that's what I am doing here. 14 and 48 are getting swapped. So 14 and 48 getting swapped means now the left pointer sees that what? Left pointer sees that 14 is less than 25. So the left pointer can move forward to 12. 12 is less than 25. So that left pointer can now move forward to 37. So this is my left pointer moving forward, and once it moves to 37, it stops there because 37 is now greater than 25. I said left pointer has to have everything less, then only it can move forward. 37 is not less than 25. So I am going to stop there. Similarly, see the right pointer. So the right pointer is here, and this right pointer starts moving left. So 48 is greater than 25. I can move left. 30 is greater than 25. I can move left. 62 is greater than 25. I can move left. 19 is less than 25. I will stop there. Right? So I will stop here with left and right, and that's where I will do the swap again. Right? So because I have stopped and left and right have not crossed each other. That's one more important thing. So unless they cross each other, you can easily swap them. So I'm swapping them, and after swap, this is what will happen. That is 19 and 37 will be swapped, and this is the final state of the array. After this, what will happen is the left pointer, which is at 19, this left pointer will see that it has to move forward because 19 is greater than 25. So it will move forward here. The left pointer will move forward here also because 5 is greater than less than 25. 19 is less than 25, so it moves forward to 5. 5 is less than 25. It moves forward to 91 and it stops there because 91 is not greater than less than 25. The right pointer, on the other hand, it will move from 37. It starts to move. So the right pointer will come from here. It will start to move from here. 37 is greater than 25. 91 is greater than 25. 5 is less than 25. So it will stop at 5. It will not move because 5 is less than 25. So now you see the right and the left have crossed each other. Right? So now I cannot swap. My job is done. When they cross each other or are equal to each other, my job is done. My job is done means my iteration is over. All I need to do is do a swap of the pivot with the right pointer location. Right? So what I will do is here I will do a swap of the pivot with the right pointer location. And when I do that, my 5 will come here. My pivot will be in the right place. And all my elements on the left will be less than 25. All my elements on the right will be greater than 25. So that is my first pass. So this is constituting my first pass. Right? And then this is not a sorted array, but it has ensured that my 25 is in the correct position, and my left pointer, the left of 25 now has the elements which are in the less than 25, and the right side has elements which are in the greater than 25. Now what will happen is next, the same routine, this same routine we will call for this subarray, and the same routine we will call for this subarray. So what are we doing? We have divided the main array into two small arrays like this, and we will now pass it to the same routine. So that now again we start doing a left pointer, right pointer on this small array. We do a left pointer, right pointer on this small array, and then what will happen is the pivot element will be this element, right? 91 will be here the pivot element, and for this 5 will be the pivot element. So they will be, after the pass is over, they will be in their correct positions. The left of that pivot element will be less, the right of the pivot element will be more, and this way it will go on. Finally there will be only one element left, and those elements will be, one element is always sorted, and then it will the whole list will be sorted. So how that happens, let us see through a code. So what we will assume here is, I'm just going back to the chat window to see if anything has come in. So if you have doubts, if you want to stop, if you have any questions, please feel free to ask in the chat window. Anyway, we will come back into the quiz mode also once this is done, so we will take a pause there also. But now let's continue with what we started. So let us try to figure out what we have done in the quick sort through a code, right? So the code and the algo will be similar in nature, and it typically comes. So we will try to figure out how to write the code by understanding the logic that we just now learned. Right? No ratta, we will just try to understand the logic and try to replicate that same logic in the code. So what we will do is, we will say that what are we doing? We are doing partitioning. Right? So partitioning is what? Shioning. Right? Is what we are doing. So if we are doing partitioning, at the pivot, once the pivot is identified in the correct location, it is partitioning the entire array into two smaller arrays. Right? So can I say that if I am given this array, and if somebody tells me the lower bound of the array, which is let's say 0 in our case, and the upper bound of the array, which is let's say 9 in our case. Upper bound is this index, right? This index. 0 is the lower bound, 9 is the upper bound. And if somebody tells me that 5 is the position of my pivot, 5 is the position of my pivot, then let me see 5 is right or not. 0, 1, 2, 3, 4. Okay, somebody tells me 4 is the position of my pivot, then can I then divide this array into two sub arrays? Of course I can do. I can say from ARR 0 to 3 is one as sub array. That is, this is 0, 1, 2, 3. This is one sub array. And ARR 5 to 9 is another sub array. Right, so ARR, this is 5, this is 4, so this is 5, 6, 7, 8, 9. So you see, from this 4, I can easily decipher 4 minus 1 is this 3 and 4 plus 1 is this 5. And the rest, lower bound and upper bound, I have kept as is. This is my lower bound, this is my upper bound, and the pivot index, this is what we call as pivot index minus 1, and this is what we call as pivot index plus 1. So if somebody tells me that the pivot will be here at this position, I can easily split that into two halves. And then again I will call it again. Now do this, then it will tell me one more index, and I will keep on doing it till there is only one element. Right, so this is the essence of the quick sort mechanism. So what we are trying to do now is try to write that code. So what are we talking about? We are talking about partitioning. So if somebody can tell me, this is that somebody that I am trying to write, that I will give the array to somebody and it will give me the position of the partition that needs to happen. That is, in our case 4. For this particular iteration, it will return 4 to me. Right, given an array, it will return 4 to me, which is the index where the partitioning will happen, which also means that at 4 the pivot element is in the right place. Right, so that partitioning function is what we will try to do. So let us see. I will write the code in C itself and not an algo, because it is very easy to convert a C code to an algo, not the other way around. So I will do the hard part so that you can yourself take this hard part and convert it into English. So if algo comes, write English. If somewhere I saw that it told you to write an algo as well as convert it into a C code, I don't agree to that style of questioning, because as I have been always saying, this is an algorithm class. It should not have anything to do with code. Your practical can have C code, but the theory cannot have C code. But that kind of question has come. So I am going to focus here on the algo front from a C code perspective. Please feel free to convert it into English. I am sure you can do that. So partition is the function I'm going to write, and I'm going to say that I have an array, int array, and I am going to pass the lower bound of the array, and I'm going to pass the upper bound of the array, which is, I will call it as high. Right, so these are the two variables I will pass, so that I can keep calling this partition with the overall array. So ideally speaking, you are not practically or physically splitting the array into half. You are just maintaining some pointers with which you can understand the split array. Your entire array still remains as is. You are just maintaining pointers to make sure that you understand what are your logical smaller arrays. So that is why these pointers are important for you to understand the sub arrays. So now if I take int partition, inside that the first step is for us to define the pivot. What did we do? We chose P as the pivot. Right, so we will select P as the pivot, which will be our ARR of, or rather not ARR, I have taken it as A. Right, so it will be A of let us say low. Right, so we have given low, so low will be 0, right, in the initial case. So pivot will point to A of low. So P is there. Now let's take the left pointer. So our left pointer is int L, and int L will be equal to our low plus 1, because our left pointer we have started from the lower bound plus 1. If you see here, we have started L from lower bound plus 1. So low plus 1, right? So that's there. Next is our R, which is the right pointer. So the right pointer is equal to my high. Nothing fancy there. It will just be directly equal to the upper bound, which is high. Right? So that's what we will do. So our 3 pointers are set. Pivot is set. Low is set. L is set. R is set. Right? Now what we have to do is we will have to keep on increasing. What? We will have to keep on increasing the L till what happens? So let us write the loop. So because we have to keep on increasing means there is a necessity of a loop. So we will say that this L will keep on increasing till L crosses R, and the actual condition, which is A of L, should be less than equal to my pivot element. So this condition has to be satisfied, then only I can move. L should be less than R, then only I can move forward, and the element at L should be less than equal to the pivot, then only I can move forward. So move forward means what? Move forward means that I will just do an L++. That is my move forward. So likewise, I will have to do this now. If L is less than equal to R and A of R is greater than P, then R minus minus. So R will move when L and R have not crossed, which is L is less than R, less than equal to R. And it will also move when R, the element at R, is greater than the pivot. So that is my R minus minus. Now why did I take less than equal to here? Why did I take greater than P here? Because you have to also count the number which is equal to the pivot. So one of these should have equal to, just to count the number which is also equal to the pivot. Right? So you cannot just leave the equal to number isolated. You could have put equal to here also, doesn't matter. But any one equal to, not both equal to's, I have put it on the less than equal to. You could have put it on the greater than equal to also. Doesn't matter. It will not affect the entire situation. So now what we have the left and right that is moving together. Right? And it will stop at some point. When will it stop? When the left is crossing R, or when this has already happened and this has already happened. I mean, this has not happened. Both of them have not happened, right? Both of them have not happened means there is no more an element. Left has stopped. R has stopped because the elements are not matching the conditions. So let us assume that left and right have stopped and have come out of the loop here, and left and right have still not crossed each other. So let us assume that left and right have still not crossed each other. So let us say not less than equal to, let us say they are less than R. If left and right have still not crossed, let's see the situation. See here, left and right have still not crossed each other, but they have moved. They have moved from here to here. So these lines have taken care of that move. Now when I say this, it is actually doing the swap. So we have to do the swap here. Right? So that's what we will do now. If left and right is less than this, then we will do a swap. We will do a swap of let's say ampersand of A of left with ampersand of A of R. So we will do a swap of A left and A R. That's what we will do here. So that takes care of this swap. So this swap is taken care of, and then again it should continue this. Again it should start moving the left pointer to the right, right pointer to the left. So don't you think we need one more loop outside? That one more loop outside will be while left less than equal to R. Right? So I will do this particular loop so that this entire thing starts again. Left starts moving, right starts moving, and if they stop again in between, without crossing each other, then this swap will again happen. Again it will keep on moving. Until what time? Till left and right cross each other, because I have given the condition of cross here. Right? When this crosses each other left and right, then only it will come outside the for loop. When it comes outside the for loop, what I will say is I will have to because left and right have crossed each other means this has happened. So then I will have to swap the pivot with the right. So I will swap the pivot with the right here. So I am outside this loop. This loop has ended here. I am outside the loop. I will do a swap of let's say ampersand of A of low, ampersand of A of low with my ampersand of A of R. So I'm swapping my pivot with my right. So this is how this will be done, and once this is done, I will complete my function. I told you this function is supposed to return the index of R. The index of R means wherever R is at that point in time, it will return R, and that is the point of the pivot, right? So that is this. This is the point what I'm talking about, that this is my R. So this point I will return so that whoever is next will know this is the next subarray and this is the next subarray where the work needs to be done. So with that, this function comes to an end, which is my partition function, right? So now the partition function is ready for us. It has to be called, right? So before calling the partition function, just let us check what happens next. So what happens next is this particular subarray is what we are talking about. The processing will start here and the processing will also start here, right? In this way the processing will go on. So let us see what is happening. So what is happening is that this, as I said, each subarray will take the left element as the pivot. Left element is the pivot, and here also the left element is the pivot, right? So that subarrays after the left element will be my left pointer, right pointer. That will be the upper bound of that array. So the array is only this much. So the lower bound is this much plus 1 and the upper bound is here. Lower bound plus 1 is this and the upper bound is this for this particular array, right? So we have taken those pointers. Now 14 has to be less than 14 has to be less than my pivot, which is not the case. So L1 stops, right? 14 has to be less. 14 is not less. L1 stops, and R1 started from here. It is going this side. It will go this side till what point? Till it gets a number which is less than 5. But 19 is greater, so it will move left. 12 is greater, it will move left. 14 is greater than 5, move left, and it reaches 5. Right? So, and it stops here because there is no more area for it to go. Right? So it will stop here, and of course 5 is not greater than 5. 5 is equal to 5, so it will anyway stop. So R1 is here. L1 is here. So they have crossed each other. Right? So they have crossed each other, and that's where my pivot and R1 will need to be swapped. But my pivot was here only. My R1 is here only. So pivot will remain here. The swap will not do anything. So this means that 5 now is in the correct position. Everything to the right of 5 is basically greater than 5. Let us see the right side, what is happening. The right side array L2 was trying to move this side. So it will keep on moving till what? Till the elements are lesser than 91. 37 is lesser than 91, move on. 62 is lesser than 91, move on. 30 is lesser than 91, move on. 48 is lesser than 91, move on. So L2 reaches at the end. But R2 cannot move this side. Why? Because it needs to have a lesser number. It needs to have a greater number than 91 to move, right? So, but 48 is less than 91, it cannot move. So R2 stays there. So if R2 stays there, then R2 and L2 have crossed each other. I said crossing also means that both of them are equal, right? So R2 and L2 have crossed. That means pivot will have to be interchanged. So if you change the pivot with 48, this is what it will become, right? So now what happens is that you will have your subarray. The new subarrays will be this subarray, and it will be this subarray. The pivots are right now in their correct position. So what is my pivot? 91 is the pivot. So 91 will be in the correct position, and my new subarray will be this. So I will now have to work on these two sublists. So when I work on these two sublists, and similarly if I go on, then what will happen is that here the 14, 12, 19 will be split into this sub-array and this sub-array, and 14 will be in the correct position, right? And when I work on 48, 37, 62, 30, then it will be split into this sub-array and this sub-array, and 48 will be in the correct position. So now we have 5 in the correct position, 14 in the correct position, 25 in the correct position, 48, 91 in the correct position. All we need to do is play around with 12. 12 is anyway one array, so 12 is anyway in the correct position. 19 is anyway one element array, so it is in the correct position. So this is also correct, right? And between 30 and 37, if you do it, then 30 and 37 will adjust itself in terms of no swaps happening, because the pivot will be the same as R, and 30 will remain here. 62 is a single element array, it will remain here. So net, that is what by dividing and conquering, right, we are achieving what we wanted to do in smaller problems. Every small array we are sorting, or we are dividing, partitioning, and making sure that the left side of the partition is less, right side of the partition is more, and in that way the small solution when combined gives me the overall solution. So if you understand the overall solution, then how will this overall solution come into the code, right? Let us try to understand that part of the puzzle. So what we will say is that we will do a void quicksort. So let us call this as quicksort, and this quicksort will take the array, and it will take a low, and it will take a high, right? So this quicksort, what it will do is it will say that till the time my low is less than high, right? So every time you will have to check your low is less than high. So till the time my low is less than high, what I will do is I will take my pivot index as whatever this partition function is returning me. So I will call partition and say, please give me the partition of A with low and high that I give you. Please give me the partition position, which I will keep inside PI. So I will keep this inside PI, partition index. Please give me the partition index. So this entire function does that only. It splits the array, makes sure the left side is less than right, and then gives me the position of the partition. So I will store it in PI. So when I store it in PI, after storing it in PI, I can call myself again. I can call quicksort again with what? With whatever I said in the beginning of this session, where I said that take A, take the low, and whatever your partition index is, subtract 1 from it. That will be your end point of the other array, the left side sub array, and take another quicksort, take A, then add 1 to the partition index and go till the high. So this is your left array, and this is your right array of the partition. I hope you are understanding y minus 1 from PI and y plus 1 from PI, because if this is my partition, then as you see, if 4 is getting returned, then the left array is from 0 to 3. That is why PI minus 1, 0 to PI minus 1. And the right side is from PI plus 1, which is from 5 to 9. So this is PI plus 1 to the high, which is 9. So when I do this, then what is happening is, one, this main code is here. This main code ensures that the left side is sorted, right side is sorted, partition is delivered to the caller. Caller says, what? You have given me the partition, please do it for the smaller array left of the partition. Please do it for the larger array to the right of the partition. Same thing, do it. So it will again do the same thing. Again it will give a partition index. Again it will call the smaller arrays again. So this is the recursive way of actually solving quicksort. So this is what you need to remember. I hope I could make it easier for you to understand. If not, try to rewind and watch again. We will move on to the complexity calculations of this. This comes quite often, so please pay attention to what we will be discussing now. When you see an array like this, let us say I have an array like this, right? And let us say that this array will be actually given to us to do a quicksort. Then what is going to happen is 8 we will choose as our pivot. So after the first iteration, what will happen? 8 will find its correct place somewhere here. All elements to the left of 8 will be lesser than 8. All elements to the right of 8 will be smaller than 8. And then what will happen? Then this 4 will find its correct place. All elements to the left of 4 will be smaller. All elements to the right of 4 will be smaller. 12 will find its correct place. All elements to the left will be smaller. All elements to the right will be smaller. Here 2 will find its correct place. All elements to the left will be smaller. All elements to the right will be smaller. 6 will find its correct place. Left and right will be smaller. 10 will find its correct place. Left and right will be smaller. 14 will find its correct place. Left and right will be smaller. So this is what will happen with this array. So what is happening, can you see? You can see that there is a balanced tree getting created. The left side subtree and the right side subtree is having some elements. Both of them have some elements, and hence we are actually talking about a balanced tree is getting created. When such a thing happens, what do you think is happening? At each of these levels, like in order to figure out that 8 is my element, right? What I had to do, I had to move my left pointer to the right pointer to the left, and therefore I might have done n comparisons. At each level, I am doing n comparisons to find out my pivot. So I am doing n comparisons here, n comparisons here. So here I am actually doing what? Here I am actually doing n by 2 comparisons to the left and n by 2 comparisons to the right. So here I am doing n by 2 comparisons to find out this 4. Right? Here I am doing n by 2 comparisons to find out this 12. Because left is moving like this, right is moving like this, the entire array gets covered. So n of that array will be the number of worst case comparisons that you will be doing. Here n is not n has become n by 2. So here n by 2 plus n by 2 comparisons, which effectively means n comparisons. So here we are doing n by 4 plus n by 4 plus n by 4 plus n by 4 comparisons, which means again here also we are doing n comparisons, right? So net here also n by 8 plus n by 8, we will get n comparisons. So each level we are doing n comparisons in order to find out the pivot position. How many levels? How many levels do we go? How many levels do we go? So if I am doing n in each level, and then I know my number of levels, then I will do a multiplication to get my total number of comparisons, and that will be my complexity, time complexity. So how many levels, how do I know? See, I am dividing n by 2. Next time I am dividing this by 2. Next time I am dividing this by 2. Till what happens? Till I reach 1. So I am dividing n by 2 to the power how many times? The number of levels, if I take as k, then 2 to the power k times I am dividing. So this is 1 time, 2 time, 3 times. So I can write 2 to the power k times if k is my total number of levels, which is also the height of the tree. So n by 2 to the power k is equal to 1 is when I will stop. So that means that n is equal to 2 to the power of k. Take log both sides. Log base 2 of n is equal to k. So what did you find out? You found out that the total number of levels, which is k, is log base 2 of n. What did I tell you? N in each level, total number of levels is now you have found out. What is that? That is log base 2 of n. So multiply these two, you will get n log n. And that is what is the best case and average case time complexity of this particular quicksort. And what is the worst case time complexity? Imagine a situation where the array was not like this. Now, unlike any other sort, please remember, quicksort is peculiar. Quicksort is peculiar in the sense everything depends on the positioning of the elements, because your choice of pivot defines everything. So if my actual array was like this, suppose my actual array was like this, and I selected this as my pivot element. So what have I given as an input? A sorted array. Doesn't matter which sorting, forward sorting, reverse sorting, doesn't matter. I have given a sorted array to quicksort and asked it to sort it. What will quicksort do? It will check this one. It will position this one somewhere. Pivot, right? So pivot is in the correct position. 1 is in the correct position. 2 is also in the correct position. 3 is also in the correct position. So are you getting a left subtree and right subtree? You are not. You are always getting a right subtree. Whenever you create a pivot, you are always getting everything to the right of the pivot as the subtree. Right? So what are you creating? You are creating not a balanced tree. You are creating a right skewed tree. And when you create a right skewed tree, what is the height of this tree? This height of this tree is nothing but n. That many number of elements are there because we could not divide it, because it was not spreading out. Only the right subtree was present, and the right subtree had to be taken to the next level. Again, the right subtree was present, right subtree had to be taken to the next level, and so on and so forth. So once we are dividing, we are not getting a left subtree because the correct pivot is already positioned. Anything to the left is non-existent because the element is already sorted in the correct position. So my right skewed tree will return me with n. So I told you, right, each level we are doing n comparisons. Each level we are doing n comparisons to find out this pivot. Here also we are doing n comparisons. Here also we are doing n comparisons to find out this pivot. And how many comparisons are we doing? The height of the tree. In our case, the height of the tree is n in the worst case scenario. So total is n cross n. N comparisons multiplied by the height is the total number of comparisons we have to do, which is n square, and that's how you get the worst case as n square. These derivations come, please rewind forward, do whatever it takes, but please write it in the manner that I have explained. Coming to space complexity, what has happened is that in terms of space, if you see here, then what are we doing here? We are calling partition again and again, right? But the main thing that we are calling is the quicksort function in a recursive manner, right? So if we are calling something in a recursive manner, then how many times we will call quicksort in a recursive manner? Log n times we will call quicksort in a recursive manner. So every level we have to call it, right? How many levels are there? Log n levels. So we are calling log n times that particular quicksort in a recursive manner, and therefore the recursion stack, if you see, first time it will be called the recursion stack. It will be called with quicksort with some parameters. Second time again quicksort will be called with some parameters. Third time again quicksort will be called with some parameters. How many times will this go on? This will go on for log n times, because it will go on that many number of times as many number of levels are there or height is there. So this consumes additional memory. This consumes a memory which is proportional to n, and the proportionality is of log n, and that is why you will have the best case and average case as log n, right? Whereas if you see how many times this stack will be filled up in the worst case is the right skewed tree, right? So the worst case is the right skewed tree. How many times will we go and call quicksort again and again? N times, na? So we will call quicksort once, quicksort next. Because it is sorted, we will have to go till the all the elements, right, will have to be covered, and therefore we will be covering n elements, not log n elements, because the height of the tree is no more log n, it has become n. So n will be the worst case space complexity of this. So this quicksort function may be using some words with order of complexity as one word. Doesn't matter, it is not proportional to n, so it is okay to be counted as order of 1. But in addition to that, it is also using log base 2 of n for the recursion memory. It is also using probably n for the recursion memory in the worst case scenario. So while it also has order of 1 for its own variables, which is not dependent on n, it also has variable requirement which is dependent on n. Hence the overall order becomes order of n, because order of n or order of log n is always greater than order of 1. So whatever is greater will be taken. So you can have an order of n in the worst case or order of log n in the best and average case from a space complexity standpoint. So that was quicksort for you. So with that, we will get into a quiz mode now. Let us okay, my video has become inverted because of the accelerometers issue, so let me fix that while I launch the video. Meanwhile, you guys can log into the video. Let me fix that for you. Yeah, so I'm opening up the quiz. Let us do a quick short quiz now. Yeah, please join. We have 39 of you, and we will start at 35. Let's see if we can get 35 registrations. 23. Rest of you, please join. 25. Some more. Who is not there? Let's see. 29. Okay, let's start at 30. One more. Good. So let's get started. 10 questions, 30 seconds each. It will be fun for you to probably see if the questions match to your expectations. Okay, Shayon, Dipendu, Shubhodip. Good. 30 of you answered correctly. 91% accuracy, 1% dynamic programming. It's not dynamic programming. Dynamic programming is different. You will learn that in the DA classes. But this is divide and conquer. Next. Okay, Ankita, good. You are displacing Shayon. I don't know, Shayan has some magic, but you are getting a super magic, I guess. Good. But then why did 3 people get it wrong? Separator, median, key, kuch bhi, yeah? We are talking pivot here which separates. You are talking separator, median, key. Not paying attention. Chalo, next. Quick sort, best case. Rumshit, Gitika, Anushka. Problem is you got it, some of you got it as log n. See, log n is the height of the tree, right? But you have to multiply with each level how much work you are doing. So each level you are doing some work, next level you are doing some work, next level you are doing some work. So each level you are doing n work because you have to do n iterations to find out the pivot. Next level you have to do n more iterations to find out the pivot. How many iterations are you doing? N multiplied by the height of the tree. Height of the tree is log base 2 of n. So then the total answer is n log base 2 of n. So 11 people who answered log base 2 of n, you forgot to multiply it with each level's work. So you are assuming each level you are not doing any work. 1 unit of work you are assuming. Right? But each level you are not doing 1 unit of work. Log base 2 of n is what? Your height of the tree. Right? So that is multiplied by each level's work. Please remember that. N multiplied by the height of the tree. So that's the answer to this. Okay, so we have Rumshit, Gitika, Anushka. Same set of 3 people, 28. Worst case is n square. Again, you are not multiplying with the height of the tree or the work. In the layer, worst case is what? Skewed right side tree. In the skewed right side tree, your total height becomes n. It is no more n log n or log n. Right? So there are n elements means your height will become n. But at each layer, you have to do n work, n work, n work. Multiply by n, so it becomes n square. So this 5 people, please correct that understanding. It has to be n square. Okay, same set of 3 people, but the problem is that I see a lot of wrong answers. Cannot be randomly chosen. It says performs worst. It doesn't say that performs anything. Performs anything means randomly chosen, right? But then if it performs worst is when your pivot is either at the left end or at the right end, which means what? The left array does not exist, right array exists. If it is at the right end, then the right array doesn't exist, left array exists. That means you are going to create a skewed tree, right? Either a left skewed tree or a right skewed tree. And that means that it will become n square. N square is greater than n log n. That is worst case time complexity, right? So quick sort worst case time complexity will be when your pivot is coming at the left end or the right end, which means that maybe the array is already sorted. That is why you are getting it at the left end or the right end. So remember this, in quicksort, if you don't get both sides of the tree after the pivoting is done, then you are in trouble. Only when you get both sides of the tree, then you can half it, n by 2, n by 2, n by 2, and hence go for log n. Right? So that's something that you need to remember. Next. Yeah, so this chapter is on quicksort, test is on quicksort, answer will be quicksort. But then I didn't mention this to you, quicksort, and we will have this as a comparison at the end of the session, where we will see all the sorts and the comparisons, and then there we will see that quicksort is typically used for caching, right? Not for any other purpose. Large data sets we use merge sort, but for caching of large data sets, without caching we use merge sort, but with caching we will prefer to use quicksort for that matter. And we will see the complexities, we will analyze them, we will understand why towards the end. Right, so the next question on your screen. Okay, leaderboard doesn't change. Answers are okay, so we will go ahead and go to the next question. Okay, so you are getting confused between array sorted and array divided equally. If the array is sorted, it is trouble, because then you will not get left and right equal. Select a left subtree, because the array is sorted, the right subtree will not be there, or the left subtree will be there, right subtree will not be there, because pivot will be at the end, right? And the pivot will always be in the correct position if it is at the end in a sorted array. There will not be a left subtree, or there might not be a right subtree. So if it is sorted, remember, quicksort is not the model. If it is not sorted and the pivot comes to the middle, that means you can now divide the array by half. Next level you can divide it by half. Next level you can divide it by half. And in this way, every level you are dividing by half means that n log n becomes your complexity. N log n is obviously lesser than n square. When does n square happen? When it is sorted. Right? Each level n comparisons, height of the tree n when it is sorted. Each level n comparisons, height of the tree is log n. So height of the tree reduces from n to log n when your array is not sorted. Median pivot is what is required. So pivot divides array equally is the right answer. Yeah, sorted is the right answer. 59%. Reverse sorted. In naive pivot, reverse sorted is not the right answer. In fact, we did not cover naive pivot. This question is ambiguous for you. While it is correct, but then naive pivot is when you are actually, naive means what? Naive means that it's basically childish. It doesn't know much. So it has got an array and it will just try whatever it knows, right? So it is only applicable for sorted. It doesn't know how to do reverse sorted. So naive pivot is only applicable for sorted. So when you get a sorted array, then only you get a worst case complexity, the right answer. Last question. Aditya has moved to the leaderboard. Good. Recursion ends in quicksort when the array size is 0 and 1. All elements are compared. Now, when all elements are compared, it doesn't mean the array size has become 0 or 1. I could compare all the elements in one layer. Does it mean the next layer doesn't exist? The next layer has some more array, sub arrays are there. I will compare that also. Next layer, one more array. Till what? Till the array size becomes 0 or 1. Right? At the last layer, I will have the array become 0 or 1. So it's not that I'm comparing all the elements. Of course, I'm comparing all the elements every layer. And that's why each layer I'm doing n amount of work. So all elements compared is not the right answer. The right answer is array size is 0 or 1. So that's our first assignment. Let's see. Okay, Shayan as usual, Rungshit good, Aditya good. Aditya has become a Yeti. The avatar of Aditya is kind of good. So you can see the class performance degrading as we went along the way because the questions became a bit tougher. Nothing much to worry about it. Play attention. I'm sure you will do good. Let us switch back to our merge sort module. Yeah. Okay. So coming back to merge sort now. So merge sort is also something that is divide and conquer. As I said, all the three sorts are divide and conquer. So this is also going to be divide and conquer. And in merge sort, what we will do is we will keep on dividing. Again, we will divide. So first step is divide and second step is conquer. So we will keep on dividing this array. We'll keep on dividing this array from half. So since this array is an odd number array, an odd numbered array, we cannot exactly divide it by half. So one of the element will be part of the left or the right array, and that's how this is 4 elements, this is 3 elements. All we have done is we have divided this array at the half point, right? Again we will divide this array at the half point, right? So this will again be divided at the half point. This will also be divided at the half point. So all we are doing is we are splitting the array. Once we have split the array and we do not have more than one element in that array, right? We will stop our divide phase. Our divide phase is done. So now we will do a conquer phase. In the conquer phase, we will merge the arrays by sorting them into this new array. This is a new array. In this new array, we will take these elements and put them such that they are sorted. Remember, we have to sort and put. Sort and put into a new array. Sort and put into a new array. Sort and put into a new array. Again, we will merge these, sort and put into a new array. Merge these, sort and put into a new array. What are we doing? We are conquering. Sort and put into the new array. This is where we do the final array. So how do we sort and put is what we will try to figure out. So let us try to figure that out through an example. Same example let us take. Let us say we have this particular array where we have 5, 29, 40 and 45. So I am taking this portion of the array, right? And let us say that the other side is giving me this array, which is 11, 12 and 84. Right? So how do we sort these two arrays and put them into a larger array? That is the question. So this larger array we will first create with that many number of elements as is required from the two smaller arrays. So the two smaller arrays, if we add the total number of elements, then we are going to get 7. So I will create 7 as my size of this particular array, right? So this is 0, 1, 2, 3. This is 0, 1, 2. Now I will take, let's say, I pointing here, j pointing here and k pointing here. Very basic thing we will do. We will compare wherever I is with wherever j is, right? And whichever is the smaller, we will put that inside the target array. So since we have put 5 inside the target array, I can therefore move forward, right? I will move forward, point to 29. J will still stay here. J will not move because we have not taken j. So 11 has to be taken. So j still needs to point to 11. So 29 and 11, which is smaller? 11 is smaller. So we will take j. Because this j was taken, I can now move j forward. But I cannot be moved forward because I was not taken. Now I has 29 and 12. So j will therefore move forward again. Because 12 is lesser than 29. So 12 will go here. J will move forward here. Right? So j will move forward here. Now 29 and 84 will be compared, and here I will be lesser. So therefore my I will move forward. 29 will be taken here. Now 40 and 84 will be compared. 40 is lesser. Therefore 40 will move here. I will therefore move forward. Right? So next, after 40, I is at 45, j is at 84, 45 will move forward, or I will move forward, 45 will be taken. I has moved out of bounds, I's loop will stop. But j has nobody to compare. So j is here. It could have been that j was here when I stopped. It could have been that j was here when I stopped. It could have been anywhere. You don't know. In this situation, j is at the end. In other situations, j could be at the middle. You don't know. So wherever j is till the end, take all the elements and put them in order inside the array. So 84 we will take and we will put them here. Now, do I need to worry about the order of 84 and the next elements in case there were elements here? Do I need to worry about the order of these elements? No, because these will already come sorted for us, because here they are being put after sorting only. So the order of 84, after that there will be somebody who is always going to be greater than 84, and so on and so forth. Last number will be the largest number. I will just blindly take wherever j is and put them everywhere. By the way, every time I am putting this this element inside this target array, my k was also increasing. Every time I was utilizing the target array, my k was also increasing, and finally my k came here, and my target, all the source elements have been covered. J has also moved forward, and j is now pointing to an out of bound kind of a scenario, and hence we will stop. So I is pointing to an out of bounds scenario, J is pointing to an out of bounds scenario, and all my array elements are fitted here. So this is actually achieved. This sorting is actually achieved. This is the core of merge sort. Dividing it by half is a no-brainer. We can easily do it. After that comes the aggregation. During aggregation, we'll have to take a larger array and put the smaller arrays into the larger array by placing them in sequence. That's the only thing that you need to remember. So let us see how we do that through code. Again, we are going to take C code, and I will assume that you can actually move forward with any code, any algorithm that is given to be extracted from that C code. So what we will do is, like previously we had partition. So like previously we had partition as the main worker, and then we had quicksort. Inside quicksort, the first step was do partition. Second step was call quicksort on the left, and the third step was call quicksort on the right. This was the three steps. So we had to take this actual worker, write the code for this actual worker, which was the largest lines of code that we had written. Similarly, here merging whatever I discussed right now, these two getting merged, or these two getting merged, everywhere where it is getting merged, that piece of code is very important. So we will have to therefore write the merge code first before we decide on the recursive approach. So if we have to write the merge code first, then we will say merge what? I will have to merge two arrays, right? But as I said, our array is not getting divided physically. We are just maintaining pointers to divide the array, right? So how many pointers do we need? So we need the array first of all, which is our A. And in order to merge, we need both these arrays. We need this array, and we also need this array. Both the arrays we need, right? And both these arrays are a part of the larger array itself, right? Both the arrays are the part of the larger array itself. Only thing is we have to give the left and right pointers properly. So what we will have to give is, what is my left pointer, what is my middle pointer, what is my right pointer. Now with this, if we do, then I can break down this array from the left pointer to the middle pointer, and from the middle plus one pointer to the right pointer. So that is how I can establish two arrays from these set of pointers. So A can be divided with the lower bound as L, upper bound as R, and in between at M we are going to divide A, right? So these are the integers that we will take as our parameters to the merge function. So what we will say is, we will say that my I, remember my I here, my I was here, right? So don't forget that my I was here, my J was here. Let me clear this up for you. So my I was here, my J was here, and my K was here, right? That's how I was actually trying to do the conquer, right? And don't think that I was not here. I was also here. J was also here. K was also here. I'm just trying to take the last step because it has more elements, just from a clarity per se. So I will say that I have to define my I. So my I will say will be equal to my L. So my I will be equal to my L, and my J will be equal to my M plus 1. So I will take J till my M plus 1, right? So I will go from L to M, and M plus 1 will be the starting point of J. M plus 1 will be the starting point of J, and my K will be starting from 0. And I will take a temporary array. This is a new array we have to create. So we have to create a temporary array. And the temporary array size will be very simple, R minus L plus 1. So in our case, this is 0, 1, 2, 3, 4, 5, 6. My R, my left is 0. My R is 6. So 6 minus 0 plus 1, right, will be giving me with 7. So I will create an array with 7 elements in case L is 0, R is 6, which actually substantiates how much of size I need. I need the size of the two subarrays put together. So that is going to be R minus L plus 1. So I need 7 spaces to actually merge the two arrays. Whatever L and R is given to us, I need 7 spaces for that. So imagine here your L is given as let's say 0, your M is given as 4, and your R is given as 6, right? I will put it in this color. L is given as 0, R is given as M is given as 4, R is given as 6. So what is going to be the size of this array? This array size will be 6 minus 0 plus 1, which is 7. So we will create a 7 pocket array like this. We will create a 7 pocket array like this, and that is what we do here. A 7 pocket array is what we create for this particular case, right? So now let us move to the next line. What we will do is we will now need to merge both the halves, right? So when we will merge both the halves, I should be, this is what? This is our M. So I should be less than equal to M is the loop that will run from here to here, and this will run from J, which is running from whatever that value of J is till R. So I have to write that I will run a loop. I will run a loop while I is less than equal to M. I will run a loop, and I will also say that J is less than equal to R. So both the conditions I will check, that I is less than equal to M and J is less than equal to R. So this is my R. So J is less than equal to R. So that basically means that my starting pointer has some space to go till the end of the array. And in this, what I will say is that if my A of I, if A of I is less than, and I'll put an equal to A of J. Somewhere you'll have to put the equal to, so you can put it on the left side, which is okay. A of I is less than equal to A of J, then my temp K, I will put it inside K, whom? A of I. A of I was less, 5 was less than 11, therefore I will put 5 here, right? So that is what is happening here. Temp K equal to A of I. And because I have put temp K and I have utilized I, therefore I should be increased. Remember that we had increased I when we utilized this 5 and put it inside here, right? We will increase the value of I. We will also increase the value of K, because K has now done its job. So K now needs to point here. So that is what we will do for this particular while. But there could be an else situation where we will say that, okay, if that is not possible, then temp of K will become A of J. So then obviously A of J is less than A of I. So 11 must be less. So 11 has to be put in the correct position. In that case, I will take 11 and put it in the correct position of temp of K. Because I have taken 11, consumed my J, J will have to move forward, K will have to move forward. Right? So that's what we will do, and then we will close the bracket. K is moving forward in both the cases. So it is prudent for us to not write it like this, but write it K plus plus here. So it will be easier for us to interpret that rather than writing K plus plus on both the sides. So that being said, that is our loop to actually position till any of them become empty. Any of them crosses, right? So if let's say we cross this particular array, while doing all of this, one of the array will get emptied. Let us say that this array is completely put here and J is somewhere here. So then the crossing has happened. This loop has come out here. The crossing has happened and this loop has come out here, means one of them, we are given both of them. See, both of them was here. I less than equal to M, J less than equal to R. Both of them was there. One of them is false, it will come out. And then the other person will have to be taken as is into the new array. So I have to take that other person to the new array. I don't know which other person is there, so I will do both. So I will say that I could have been here, so then I have to take this and this, or J could have been here, then I have to take this. So I don't know which of them has exited. So I will say that wherever I is right now, I will again run a loop from I. If I would have exited with I crossing M, this loop will not enter, which is okay, right? So I will say I less than equal to M. I will do the same thing that I did earlier. So I will do temp. I will do temp K equal to my A of I, and then I will do I plus plus and K plus plus. I will also do a while loop with J less than equal to M, because as I said, I don't know, this could have exited at I here, or J could have exited at or I could have exited here because it is out of bounds. Therefore J would be remaining, and we have to run a loop for J, and we will say temp of K equal to A of J. We will take that element, increase the value of J and increase the value of K, and end the loop. That is what we will do for the remaining elements, copying into that element. Last step that will be left will be, I put the last step here. The last step that will be left is that after all of this is done, this temporary array needs to go back to the main array, right? So the temporary array needs to go back to the main array, and it's a very simple loop that we will run. We will say for I equal to L, K equal to 0, I less than equal to R, I plus plus, K plus plus. So we will run a loop where we will say that we will position I to the lower bound, and we will take I till the upper bound, right? And we will increase I and K. So there are two arrays like this. One of the array is governed by I, one of the array is governed by K. So we will take this element, put it here, increase both. Take the element, put it here, increase both. Take the element, put it here, increase both. That is what we are doing here, right? So we will say A of I is equal to temp of K. That way the entire temp gets copied into A of I. So this is this part, right? So as I said, in our case the actual work was being done in the earlier case by this partition function. Then the quicksort function called itself. Now our actual work is done by this function, but this function therefore needs to be called, right? So let us do that part, and that would complete the algorithm. So in that part, what we will do is we will say that merge sort is a function. Merge sort is a function which accepts int A, which is an array, int L and int R. And inside merge sort we will check L less than R. If L less than R, what we will do is we will calculate the midpoint. Partitioning has to be done, right? So nobody did this partitioning. Here what it did is it just merged this particular code, just merged everything. It did not do partitioning. Now we have to do this partitioning, right? So that partitioning will be done through this particular code, where we will say that my midpoint is going to be let us say L plus R minus by 2. Now I will put a question on the chat window. Why did I do this? I could have easily done R minus or L plus R by 2. I could have easily done L plus R by 2, and that would have also given me the midpoint. Instead I did L plus R minus L by 2. Why did I do that? In the chat window. Anyone? Midpoint is L plus R by 2. I did not do it. Anyone? Okay, so this is an important question for you to understand. I'm not sure if in your class this has been told, but when you are doing L plus R by 2 to calculate a midpoint, then this L could be an astronomically large number. Adding R to it will make this astronomically still larger. So you might exceed the bounds of an integer, or you might exceed the bounds of a long. So L plus R will increase the bound, right, for that particular data type, and it becomes out of bound. If you do this, then what are you doing? You are actually doing L plus R minus L by 2, and that way you are not adding a large number to L, and therefore the chances of you crossing the bounds will be much lesser. So that is why we do L plus R minus L by 2 rather than doing L plus R by 2. So R minus L will narrow it down, divide by 2 will further narrow it down, add it to L, you will get the midpoint. So that is the reason for this midpoint. After this midpoint is done, what we will do is we will say that merge sort, we will call the same function. We will call the same function merge sort with A, L and M. That is my midpoint, L and M. And then also again, that is the left part, right? A left, the left pointer to the midpoint is the left array, right? So then we have got the midpoint, so we are dividing it into the left array. So this is the division that is happening. Here we are dividing it to the left array. Here we will divide it to the right array. So the right array will start from M plus 1 and go till R. So therefore we have merge sort both the things, and so it has divided both the arrays. Now after the division is done, at the end it should be aggregated. Therefore the aggregation is already written for us. We have already written the aggregation. We are now going to call that as A left middle R. That's it. So that's your merge sort algorithm, where we are saying that, okay, I have divided both the arrays at the midpoint. Each array I will combine using the function that we have just now done, right? And to combine that, we need to pass it the left, mid and the right. And we all know left, mid and right now. So every time if we actually do the same process, every time we are doing the same process on the smaller array on the left, the smaller array on the right, then merging it. Again doing smaller array on the left, smaller array on the right, merging it. So this is how we are continuously doing whatever we are trying to establish here, right? So that is on this particular merge sort. Now if we move on to the complexity of merge sort, it will be almost similar, because again here there is a guarantee that, let's say if this is n, you are dividing it at the half point. So the next element becomes n by 2, the next element becomes, next layer becomes n by 2. There is a guarantee that here again you are going to divide by half, so the next element will become n by 4, and the next element becomes n by 4. Here also it will become n by 4 and n by 4. So in quick sort, there was no guarantee that the pivot will be at the middle, but here we are doing it at the middle because we are calculating m. So every time m will be at the middle, therefore each element, each layer, each subarray will be divided at the middle, and therefore this will always be log of n in terms of the height. And each layer we will be doing n work. Therefore, n multiplied by log of n will be my total complexity. So this is going to be my total complexity. There is no worst case as n square. This was the worst case for quicksort. Because quicksort was not sure where it might end up, where the median might end up. It could have ended up anywhere. In a sorted array, it ends up at the left or at the right, and therefore the middle portion bifurcation was not happening. Here, the middle portion bifurcation will always happen, middle portion. Every time you will divide it by half. Hence, the height of the tree cannot be anything other than log base 2 of n. I have proved that in the earlier example. At each layer, we are doing n amount of work. Therefore, n log base 2 of n is the total complexity. From a space standpoint, remember you are taking a new array. Remember here, you are taking a new array. And this new array depends on n, doesn't it? So I told you if it depends on n, that is where you have to be careful. That because it depends on n, that is the extra space you are taking. You might be taking order of 1 for your own work, but at the end you are also taking an order of n because of that temp array, the new array. Therefore, these two put together will be order of n, and that will be your space complexity for merge sort. So that is merge sort for you. So before moving to heap, let me see the chat window. Okay, nothing much. Let us move on to the quiz. So please scan the merge sort quiz. How many of you are here? $37. Okay, let's see 30. Please scan. Yeah, should be visible now. Please scan. Six more. Four more. Three. Quickly. Okay, let's start. Okay, I have a new name, Shomili, good. Shreyan, good. Rungshit, good. You are maintaining the consistency. 3 people still got it n square and log n. Please correct it. It is n log n. n times it does work at a particular level. How many levels? Log n levels. So n log n. Top 5 for the marathon will be getting a small token of gift or a goodie bag. I'm going to arrange for that probably before your exams only, along with the MAKAUT certificate. So keep participating. Yes, this is right. Shreyan Rungshit Shomili, leaderboard has not changed. More or less 73%. I'll move on. Yeah, I think I knew that depends on input will create a confusion. Divides an array into how many sub-arrays at each step? At each step it only divides it by half. Sub-arrays are divided by half only, na? Why are you saying depends on the size? It doesn't depend on the size. Every step, one step down, it has divided it by half. One step down, it has divided that further by half. So why should it depend on the input? Okay, good. 31 of you answered this correctly. Nice. Merge sort is a stable sorting algorithm because it preserves the sequence of duplicate numbers. The only algorithm that changes the sequence of duplicate numbers is selection sort and quick sort, and even heap sort for that matter. So quick, heap and selection is the sorts that is not stable. So from what you read in class in the last semester, you will pick selection, and from what you are reading in this semester, you will pick quick and heap sort, right? To say that these are not stable. Rest everything is stable. It maintains the original sequence of the numbers. Yeah, now here you'll have to be Gitika Kashyap, good, you have come up in top 3, but here you have to be careful, right? In an array, is it easy to divide the array by half, or is it easy to divide a linked list by half? Linked list, how do you know the half of the linked list? You can't. You have to traverse the entire linked list to know the total number of elements to know the half. So linked list, you don't know the half. Array, you can easily know it because you have the upper bound, lower bound. That's why array is the right answer. So in merge sort, because you have to half it, you cannot use, or you can use linked list, but it will be time consuming to actually go through the entire linked list to know the where you have to divide it. Okay, leaderboard doesn't change. Space complexity is n for a merge sort, because in a merge sort we are talking space, we are not talking the levels. So log n cannot be the answer. Log n is only useful for time, not for space, right? And order of 1, whoever answered order of n log n, I'm going to take that as redundant answers. Order of n because I'm defining an array, temp array, and that is giving me my n. The rest doesn't matter. I've already given you this answer. Yeah, I knew there will be mixed. Shudojit, Pratyush, good. See, I already gave you this answer. Merge sort is preferred over quick sort when array is nearly sorted. Now, nearly sorted, yes, because quick sort will run into danger when the array is sorted. But more than that, I told you, right, the benefit of merge sort is that it does a stable sort, which means if there are duplicate numbers, then it maintains the sequence. Which do you think is important? I had, let's say, a same name as somebody else. I was standing in a line before that somebody else. After sorting, my sequence changed. Do you think that is more important than time? I'm okay to wait for additional time, but I'm not okay to change my positions just because my names were same. So, what is more priority here? Both are right. 16 and 12 of you who have answered this, both of you are right. When the array is nearly sorted, quick sort will take more time. It will not be log n, it will be near to n square. Right? So both of you are right, but I'm okay for time, but I'm not okay to swap my place with somebody else. Isn't that the normal human psychology? That will apply to any physical realm. Any entity it will apply. That you cannot change the sequence of how they were. That is more important than doing it quickly. Hence, stable sort will be the right answer. Okay, Surojit Patro knew. How many levels of recursion does merge sort have? Levels of recursion. Recursion happens at each level. N log n is not the levels. Level is the height of the tree. Height of the tree is log n. N is at each tree you are doing some iteration, some for loop is running. That's not recursion. That for loop runs for n. That's why each level there is n work being done. But then recursion is every level you have to call merge sort again. Every level you have to call merge sort again. So how many levels are there? The height of the tree. Height of the tree is what? Log n. So the answer is log n. N is a multiplier for each level's iterative work. There is nothing to do with recursion. Okay, Pratyush, good. Bhavya and Surajit, you are anywhere there. 52% accuracy, original array. During merge, elements are copied to the original array. No, when we are merging, there are two arrays. We are merging, we create a temporary array. 22 people answered it correctly. Original array, we cannot, right? Original array is small. The left array is small, the right array is small. Adding them is what we are talking, right? How can you add them by utilizing the same arrays? Same array is not giving you that space. You have to create one array which is a combination of the space of both the smaller arrays. That is why you need a temporary array. Twenty-four of you answered it correctly. It cannot sort. Linked list is not the answer. It can sort. You have to take more time. You have to go through the linked list and find out the middle element. It can sort. It's not that it cannot sort. But it requires additional space because merge sort is known for wanting to have a temporary array, which the others don't need. It is not stable is not correct also. It is stable. It is faster than quick sort. No, it is the same, right? It is the same order of n log n. So those are not the answers. So that's this merge sort assignment. Not good performance. Shayon, Pratyush, Bhavya, very good. So let's see the class performance. It would be okay. It's more or less average performance. That's okay. So let's move on to the last part of sorting, where we will talk about heap, and then we will quickly cover the complexity of various kinds of sorts and move on to the Q&A of heap, and after the Q&A of heap we will cover the frequently asked questions in your universities that we will talk about. So heap, I had already talked about heap at length in the last marathon session. Some of it I am going to cover just to explain you heap sort again. So heap is what you need to understand for heap is, what is it? It is a complete binary tree. A complete binary tree first of all means that it should have all levels filled up except for the last level. Last level there is an exception. So this level, how many nodes is possible? 1. In this level, how many total nodes is possible? 2. In this level, how many total nodes is possible? 4. So 1 is filled up in this level? Yes. 2 is filled up in this level? Yes. 4 is filled up in this level? No. Allowed. Because this is the leaf level or the last level. So in this case, this is a complete binary tree. So if this is a complete binary tree, one more item that we need to remember is that the level that we are filling up should be filled up from the left to the right in a complete binary tree. So I cannot have something like this. Let's say I cannot have something like this. So what needed to happen? I needed to have the node here, and this was not something that I will allow. This node should be here because I am doing a left to right. I'll have to fill up every layer left to right before moving on to the rightmost, right? And every layer has to be filled up completely before moving to the next layer. The last layer can have empty elements. This is what is a complete binary tree. Now what makes this complete binary tree a heap? The complete binary tree is a heap when its descendants, when the descendants of a particular node is always less than the parent. It's not the children, mind it. All the descendants will be less than the parent, and that is the difference between a binary search tree and a heap. In a binary search tree, the left should be less than pivot, should be less than the right. But in a binary in a heap rather, the entire of the left right doesn't matter, the entire descendant will be less. When will it be less? When we are talking about a max heap. A max heap means that the highest element will be always at the top of the heap, and a min heap is the reverse. So a max heap is the highest element at the top of the tree, and every node is greater than its descendants. So if I see this, then I see that every node is less than the parent. So every node here is less than the parent. So this is what makes this a max heap. Of course it is a heap, but it is also a max heap. And if you do the reverse, where 25 will come down and 3 will go up and the other nodes will also adjust itself, you get a min heap, right? So if we go to the max heap and min heap, this is an example of your max heap, where we are saying that if this array is to be converted to a heap, then by the process of heapify is what we will convert this into a max heap. And when we convert that to a max heap by the process of heapify, we will be getting this particular tree, and this tree is a max heap because every node below it has all lesser elements. Every node below it has all lesser elements. Every node below it has all lesser elements. So that is why your this becomes a max heap, and 91 is actually your highest element. The way it is structured, right? If the max heap is structured like this, there is an advantage, and I'll give you that advantage 5 minutes on into this conversation. So what is a min heap then? The same but ulta. So the lowest number will be at the top. Every node below it will be greater. Every node below it, every node below, right, of 10 will be greater. Every node below of 15 will be greater than 15. Every node below of 37 will be greater, and so on and so forth. So that is your min heap, right? So this is max heap and min heap for you. Now let us try to figure out how do you heapify a particular sequence. So if this sequence is given to you, you have to heapify this sequence, and how do you do that is what we are trying to discover. So this is called insertion process. Somewhere you will see another process where the order is n, but we are now going to talk of an order of n log n, which is going to be lesser than n, and hence I am talking about that. So sorry, this way, right? So n is greater than n log n. I will not talk about the heapify process, which is going to give you a complexity of n. I am talking to you about a heapify process which relies on, it's called insertion way of doing heapify. Right, so the insertion way of doing heapify will give you a n log n, and that is beneficial because to create this heap you require lesser amount of time. Right, so with this, if I start heapifying this particular or creating this heap, heapify means create the heap from a sequence of numbers, as simple as that. Right, so if I take 10, I will put 10 first here. Right, so 10 is gone. Next I will put 20. So I will place 20 here, and then I will see if this is a heap or not. Because my first aim is to make it complete binary tree. Complete binary tree is move on to the next level, because the first level is already consumed with one node. So I'll move on to the next level, which will have 2 nodes. So I'm free to put 20 here because this is empty layer, and I have to put it from left to right. I cannot put 20 on the right of 10. I have to put it to the left of 10. So I'm actually following the rules of a complete binary tree. But is it following the rules of the heap? The heap says and I have to build a max heap. By the way, I have to build a max heap. So the heap says that my largest element should be at the top. So in this particular small chotku example, this is a tree. Is the largest element at the top? No. So I have to swap 20 with 10. So then this will become 20 and this will become 10. Now this for me is, this small tree is a heap, right? Because it is a complete binary tree plus it is a heap and it is a max heap. So the next element is 15. So the only area I can put 15 is here. I cannot go down, otherwise it will not be a complete binary tree. So the only area I can put it is here. Now putting it here, does it disturb this to be a heap? No, because all the elements below 20 are less than 20. So this is perfectly valid heap, right? So let us move on to the next. Where will we put the next? So the next is coming is 5. So if I take this 20, 10 and 15 here and then 5, then 5 has to be of course put here, left to right I have to put, and 5 being here, is it valid? Of course it is valid. Every element is less than 20, every element here is less than 10. So 5 of course here is valid, right? And then if I take 30, then 30 will come here. Is this 30 good? This 30 is not good, because this is violating that every element below is not less than 10. So 30 has to go up. So let's move 30 up. So 20, 30, 5, and then we have 10 going down, and we have 15 coming here. Now, is this complete binary tree? Yes, of course. But is this a heap? No, because 30 has to go up, because this portion is not completely less than 20. 30 is still here. So what we have to do? We will have to change 30, move it to the top, bring 20 here, bring 5 here, bring 10 here, and bring 15 here. So that's what we will do. And this creates for me a max heap here, because all elements below 30 are less than 30. Now 30 is also done. 25 we have to put. The only area we can put 25 is here, right? But is it disturbing my heap? Of course it is disturbing my heap, because my element below 15 is greater than 15. Max heap doesn't allow. Parent has to be greater. So therefore I will shift this now from 30, 20, 25, this is 5, this is 10, and this is 15. Now is it a max heap? Yes, because I can see that all my elements are less than 30, all the elements here are less than 20, all the elements here are less than 25. So this basically is a max heap, which is same as this answer. This is how you will build a tree. Now what did you do while building a tree? While building a tree, what did you do? You took an element and you inserted it here. Now the worst case situation is this element will have to travel right to the top. Here this exactly 25 traveled one layer. But remember 30 here, it traveled one layer, then it again traveled one more layer. So the worst case is that it will have to travel all the levels. That means the worst case is that it will have to travel all the way to the top, which is the height of the tree. So the worst case, what is the height of a tree that is divided like this? Complete binary tree means it is divided equally. So height of the tree will be log base 2 of n. We have established that, right? The complete binary tree will be log base 2 of n. Right? So log base 2 of n, if it is the height of this particular tree, right, then this log base 2 of n will be the complex, will be the worst case complexity of the number of levels that it has to go up. So every node has the risk of doing this. Every node has the risk of doing this. That is what is worst case, right? In case this 5 was not 5, was something else, then this also had to go like this. So if every node has to do log base 2 of n, then we are going to say n multiplied by log base 2 of n, because there are n nodes, is the total complexity of the building a particular heap. Heapification process by insertion logic will take n log n. So that is building the heap. And now we come to the actual topic, which is heap sort. So now that we have built the heap, how do we sort this heap? Sorting this heap is easy because this heap has been carefully built. What is carefully built? Entire this thing is less, entire this thing is less, entire this thing is less. So there is a arrangement of ascending or descending inside this tree itself. If we can tactfully take out the elements, we can create a sorted list from this particular tree. So we will now tactfully take out the elements, but before that, let us say that this is a tree. A tree is a graphical form, right? If tree is a graphical form, then I cannot represent a graphical form in my code. I need a data structure to represent the tree. Let us say that I have an array to represent a tree. Then in this array, what I will do is I will go top to bottom and left to right. So I'll go left to right first, then slowly go bottom and cover all the elements. So if I do that now, what is the element that I get? Top 30. Next element I go down left to right 20. Next element I go down 25. Next element 5. Next element 10. Next element 15. This is how I will store the tree in my data structure. Now I can process this tree. In order to get my heap sort. How will we do that? In heap sort, the mandate is just like in stack, right? You have the mandate that you will have to pop out the topmost element. Here you have the mandate that you can only disturb the topmost element. So I will take out this topmost element, and that is called as deletion of the tree. So deletion is the process with which you will do the heap sort. So I will delete 30. So I have created a tree painfully, and now I am going to delete it to create a sorted list. That is the entire process. The creation of this tree, I told you how we did it. We did it like this. And once we have created it, we are now deleting it. And deleting doesn't mean delete any element. You can only delete the top element. So the top element I will delete. And when I delete the top element, what will happen is the lowest element of the array will move to the front and replace the top element. And this space will become empty. So if I draw the tree for you now, the tree will look like this: 15, 20, 25, 5, 10, 15. Actually 15 is not there, 15 has moved up. So I have deleted 30. So this 30 is deleted and is no more a part of this tree. And instead this 15 has moved up, right? So this 15 has moved up and taken its position. So how does the array look like for us? So let us draw the array. The new array now looks like this. 15 has come here. So 15 has come here. And then we have 1 minute. Okay, so whenever a call comes, the gyro sensor rotates me. I don't know what affinity it has with me. Sorry for that. So 15 goes there. And then we have 20, then we have 25, then we have 5, then we have 10. But this space, I told you this 15 has gone to the front, 30 is deleted, so this space becomes free. So in this free space, instead of killing this 30, I will put this 30 here. I will temporarily store it, because that space is anyway available for me, na? But the array, don't worry, the array is having the size of this now. The array has become small. And this wasted space of the array, I am putting this killed element here. right? So that's what I'm doing. So the next step is to make this heap a heap. This is not a heap. This is not a heap because 15 is at the top and at the bottom we have 20, 25. At the top I should have the largest element. We are talking about a max heap here, right? So if we do that largest element concept, then what happens is 20 and 25, 25 should move up. Both of them are greater than 15. Who goes up? The highest element will go up. Right? So if 20 and 25, the highest element goes up, then this tree will look like this. This tree will look like 25, 20, 15, 5, 10. Right? So this tree will look like this. Is this a heap? Of course it is a heap. All the elements here are less than 25. Then how is my array going to look like? So my array will be looking like this, that it will have 25 here, 20 here, 15 here, and 5 here, 10 here, and of course this portion was blank where I had put 30. So my array looks like this. Now if this is a sorted, this is a heap, proper heap. So I can now start again the deletion. So what will I delete? I will delete the topmost element. And what will I swap? I will swap the last element in that topmost element. Right? So let us do that. So the tree will actually look like 10 will come here at the top. Then underneath of 10 we will have 20. Then we will have 15. Then we will have 5. And our array will look like this. Our array will look like this, which will have 10 here, 20 here, 15 here, 5 here, and then the array gets completed because all the nodes are taken. So now we have 2 positions empty. Originally we had 30 here. One more position became empty. This killed element 25 we will position here. Whatever element we are killing, we will put it inside the wasted portion of the array. The array has reduced because the tree is right now a reduced tree, right? So the array is also reducing. Right? So 25 is here, but this is not a heap. This is not a heap because we have elements which are greater here than 10. So we'll have to convert this to a heap. So let us convert this to a heap. So we will say between 20 and 15, 20 will move up. Then we will have 10 here, 15 here, 5 here. The array will change. The array will look like this, which is going to have 20 here, 10 here, 15 here, 5 here, and the wasted portion of the array was already holding 25 and 30. So this is how the array is going to look like, and now we have a proper heap where all the elements below are less than 20. So now we will again do a deletion of this particular topmost element. I will delete this element, and who will I move? I will move the lowest element into the front of the array. Right? So that is what we will do, and we in fact to do that, our tree should look like 5 has moved to the top and 20 has gone out. So 10 is there, 15 is there, 5 is there. 5 is no more there, so 5 has moved to the top, so this link is not there. So therefore the array right now looks like this, that we have 5 here, we have 10 here, we have 15 here, and we have the original wasted portion of the array. So there is one more wasted portion of the array which got created. In that we will put this 20 that we deleted. So we will put 20 here, and 25 and 30 was already there in the wasted portion. So 25 and 30. And in this way, if I go on, then 5 will have to be deleted. By the way, 5 cannot be deleted because this is not a heap. right? So we will have to make this a heap. So this is greater, so that is not a heap. So let us make it a heap. So in order to make it a heap, 15 will go to the top, 5 will come down, 10 will come down here, and that makes it a heap, a proper heap, which changes the array, and therefore the array will now look like this, which is 15 is here, then we have 5, then we have 10, and after that the wasted portion of the array starts, which is 20, 25, 30. Right? So then the last step is there, where we have to take this 15 out, which is because we will be deleting this 15. So we delete this 15 means who comes? 10 comes and replaces this. So 10 comes and replaces 15. And beneath 10 we have 5. So 15 is not there, and therefore our array looks like this. Okay, so our array looks like this, where we have 10 here, 5 here, 15 has gone out. So 15 now takes the wasted portion of the array. So 15 is here, 20 was already wasted, 25 and 30. Right? And then the last step is 10 will get, this is a heap. So of course this is a heap. I can therefore delete 10. So I will delete 10 from here, and I will therefore have 5 as my element, right? The only node that will remain is 5, and because 5 replaces, because 10 goes out, 5 can replace, right? The same logic, and therefore our array will look like this. At this layer, our array will look like this, which is 5 is here, and then we have the wasted portion of the array starting, which is 10, and then we have the older ones, which were 15, 20, 25, 30. And because 5 is here, 5 will replace itself if we delete it. So 5 will now occupy the wasted portion in the next stage. So now what you have here is the sorted array: 5, 10, 15, 20, 25, 30. So that's the entire process. Heap creation is order of n log n, which we saw earlier. Each delete will take log n. Why? Because each delete, when I am deleting this 15, is moving up, right? The first step, remember, we move 15 up. Now what is happening? Can this 15 come all the way down? Yes, it can, because if it prohibits the heap, it will obviously come all the way down, and some element will move up. So if it comes all the way down, how many levels is it traversing? It is traversing log n levels, right? Because the height of the tree is log n. So the each element, when deleted, will take log n maximum complexity. And how many elements we have? N. How many elements are we deleting? N. So each element may take n levels down, it might come. So log n, and each element, there are n elements, so n log n will be the total complexity for the deletion. So what is happening is, you have from the heap creation, n log n, and for the deletion you also have n log n, right? And by now you should know that both of these put together will also be n log n. You don't say 2n log n, right? It is n log n. So that is on heap sort. The complexity comparisons, let us do it before we jump to the quiz, and after that we will complete the questions. So if you see the complexity comparisons, then this is what you had done earlier in your last semester. This is what you are learning now. So if I see bubble sort, insertion sort, selection sort, if I put all these three in one bracket, right, obviously I see that the selection sort is going to take much larger time when the best time is compared, right? But all of them takes order of n square in the other cases. Why best time of bubble sort and insertion sort is n? Because if the array is sorted, bubble sort and insertion sort can be coded intelligently to make sure that it comes out after the first iteration. Therefore, one iteration only it will have to do means n. So that is why n. But in selection sort, we cannot do that one iteration and come out. We have to go through the painful process of n square. 2 loops have to run completely. So that is why selection sort, even if it is sorted, it will take n square amount of time. However, if you see here, wherever we see the space complexity, the space complexity of all of them is order of 1. Right? So it is going to take no ancillary or auxiliary for that matter space additionally, and all of them will not be stable. I told you selection sort will be not stable. The way to remember it is selection sort has some exceptions. One exception is that it still takes order of n square in the best frame. It still takes not stable. That means sequence will not be maintained, and all the sorts will take in place memory. That is, it will utilize order of 1, which is in place memory. It will not take memory equivalent to the size of n. Right? So that is why I say that in place is yes for all of them. So if you see, bubble sort is rarely used. Bubble sorts is rarely used. Very small or already almost sorted array. It is simple and adaptive. It is more educational in nature. People don't use it. Right? And it is inefficient because of its order of n square. But then everybody is order of n square. So here insertion sort, small or nearly sorted database online, because it is stable, in place, and runs order of n when the disorder is minimal. Now if you have to remember this, you have to remember insertion sort is what? Insertion sort, if you remember, it looks like this. You have this. Let us say 4 people are standing. These are their heights. A fifth person comes and his height is this. Right? If I put this height judiciously, I will put this height here. What am I doing? I am doing insertion sort. That is, at the time of insertion, I am maintaining that order of height and putting it here. So if you are not disturbing the entire sorting process and just shifting the array, then please use insertion sort. Do not use any other sort. If this is the case where you will just have to put somebody inside, you will use insertion sort. So that's on insertion sort. Quick sort, if you see, I told you, right, quick sort has the inherent disadvantage of if the array is sorted, then the partitioning is not proper, hence it becomes n square. And quick sort also does not do a stable sort. So whoever is having a disadvantage on time is not doing a stable sort. That is something by which you can probably remember. Right? And merge sort, if you see, a merge sort is where you will have the maximum people coming in and asking you to do the problem using merge sort, because it is very powerful. It does not have any hunger for, it is stable. It is going to be done in n log n irrespective of the time taken. However, if there is a necessity to choose between merge sort and heap sort, then you will always go with merge sort if memory requirement is less. Heap does not require that much of memory as merge sort requires, because merge sort creates a temporary array. Always remember the benefit and discredit of a particular sort. Benefit of merge sort is always n log n. Discredit is it takes a array, which means the space complexity becomes order of n. So that is in a nutshell the complexity comparisons. Please remember this table. In one question they have asked you to write this table also. All the 6 sorts, they have asked you to write this table with all the parameters that I am talking about. So please remember this table. There is nothing to ratta. If you just read it and understand what it is trying to say, I hope you can probably reproduce it without even doing a mugging up. So we will shift to the commonly asked questions, but let's finish off our quiz first. One more call has come. I don't know who is calling. Okay, so let me open up the browser. So heap sort quiz coming up for you. Last quiz. And after this 15 more minutes we'll complete the questions. Please join. How many are here? 35. Let's see, 30 of you. Come on, 5 more. Okay, let's start off. What happened? Bebek, Shayon, Bhavya. Vivek, I'm seeing you for the first time probably. Good. Binary search tree. No. Heap is not a binary search tree. I clarified that heap is heap. Binary search tree has the left and the right. Left should be less than the pivot or the node, and the node should be the right should be greater than the node. That's binary search tree. But heap has everything less if it is max. So heap sort is based on which data structure? Where can you do heap sort? On heap. Now heap is a data structure. So the answer is heap for this particular example. How can it be binary search tree first of all? Heap sort is not on a binary search tree. Heap is not a binary search tree. I clarified that categorically. We have done this right now. What was the heap we used? Yeah. So if it is a max heap, Dipendu might be good. If it is a max heap, then only you get a ascending order. If it is a min heap, you will get a descending order. So remember the example we solved, 5, 10, 15, 20, that is ascending order. Which heap did we start from? Max. So max is the right answer. Okay. So net 90% of the times heap sort, merge sort, quick sort will be n log n 90% of the times, right? And the remaining 10% of the times, those exceptional scenarios you'll have to remember. But this is those 90% of the time, it will be n log n only. Again, the same thing, it will be n log n, not log n, because each element can take traversal time. Even in best case, it will take that. It doesn't depend on the ordering of the sequence, right? Because heap is a heap. At the end of the day, you are starting to work with a max heap or a mean heap. So best case, worst case, average case, you'll always work with the data which is already in a structured manner. Same structured manner, best case, same structure, worst case, same structure, because you have to work with a max heap in order to do heap sort. Right? So it doesn't depend. The data will always be in a normal heap max manner for best case, worst case, average case. It will always be n log n. You are getting confused, all of you. 14 of you answered no, which is incorrect. You are getting confused because I told you, right? Heap sort. Let us check what we have in the what we have here. Just now we have done this. Heap sort stable, no. Quick sort stable, no. Okay, I was getting confused myself. 1 minute. Yeah. Yes. So stability. In fact, I mentioned this in the beginning part of the discussion that what you learnt in the last semester, one of them is not stable, which is selection. What you learnt in the current semester, two of them is not stable, which is quick sort and heap sort. So my bad. The people who have answered heap sort is a stable, no, that is correct. 14 of you have answered correct, but the 13 of you, please correct your understanding. Heap sort and quick sort are not stable, right? So the next thing, this you should be able to get 90% of you. Let's see. Okay, so I have to switch on the browser. 1 minute. Yes, most of you got it. But 6 of you still got it as n. It's order of 1. We don't use anything in heap sort. We just swap. That's all we do. So the heap is already there for us to consume in terms of memory, right? The memory is already given in the heap. The nodes are already there. We don't use or create any additional nodes during heap sort. The nodes are already there. So what elements do we use? Standard elements. It doesn't depend on n. If it doesn't depend on n, then it's an order of 1. So that's why 21 is the 21 of you have answered correctly. Yes, heapify, and I'm sure the others might be a typo or something, but then heapify is the process to maintain a heap. The swapping that we were doing, that is heapify. The largest element is placed at the end of the array. This is heap sort. So when we are sorting, not heap. Placed at the root is when you are at the heapify process. We have been talking about heap sort. When you are doing a heap sort, if it is a max heap, the max heap word should be mentioned in this question. And that max heap, someone has raised his hands. I'm not sure how to figure out who has raised the hands. Please type in the chat bot of the YouTube link. This interface, I don't know how to get to that raised hand. But yes, I'm talking about heap sort here. Heap sort means after the sorting, the largest element is where? At the end of the array. The wasted portion. And I agree that the max heap word should have been there in the question. But why did you answer placed at root? Because probably you thought that if it is a max heap, then the heaviest element is at the top. That's why you said placed at the root. People are not talking about the heapify process in this problem. People are talking about heap sort. Heap sort will place the largest element at the end of the array. 8 of you only answered correctly for this. Ishani has come up good. Heap sort is preferred when memory is limited. Heap doesn't take memory. Absolutely correct. Right? Stability required. Heap sort is not stable. Just now we have seen that. So why did 5 of you answer this? Memory is limited is when heap sort is preferred. And that's why I'm saying that table is important for you to probably not mug up, but understand. Otherwise you will not be able to answer such questions. Fill in the blanks they might give and you will not be able to answer. Good. You have assumed max heap and then said maximum element, which is fine. So we will end the assignment here. Oishani, Bhavya, Roomsheet, good. So we have new names here, new faces here other than the last quiz. These quiz will be now aggregated and I will publish the aggregated response. Accuracy has improved as we went along the way, which is also good. So thank you for that. Let us complete. Okay, so Partho says, sir, can you repeat the stability part? So stability part is the part where we talked about Stability part is the part where we talked about that if an array actually has, and let me show it on the screen for you. So let me move on to the OneNote, and there, when we started doing this session, we talked about stability. I'm not sure if you attended that portion. So this is stable sorting, and in stable sorting we have said that if my input is like this and I have to sort this on the basis of the first number 5, 3, 5, right, and I said that each of these is one unit. 5 and A is a key value pair, 3 and B is one key value pair, 5 and C is one key value pair. So what do you see? You see that the key is the same, right? And you have been asked to sort it. Of course the sorting will take 3 at the beginning because 3 is less than 5. But what will happen to this 5A and 5C? They are both the same. So then can we preserve the order in which they appeared, so that 5A appeared first, so they will also appear first in the sorted list? Can we preserve the order of 5C? Can we preserve the order of 5C also, that it appears last? Then it is a stable sort. So if after this sort 5A and 5C are one after the other in the same order as they appeared in the original list that was given to you, then you are having a stable sort. Otherwise it's an unstable sort. So I hope, Partho, that question is clear now. Aditya is saying that there are questions in MAKAUT where they have, yes, there are questions in MAKAUT where they have said that you implement this in C, and as I said that I don't agree to that style of questioning, but it comes and I can't help it, you can't help it. So C may or may not come, but in case you don't know C, please don't shy away from writing the algorithm. If there are instructions to the examiner that if people have not written it in C and have written just the algorithm, then give them let's say 70% of the marks, right? Then you will get 70% of the marks, right? So do not shy away from writing the algorithm in case you don't know C. Now what is left is the questions. Let us quickly finish that. We have 15 minutes and we'll finish in 15 minutes only. So because most of the questions are already covered, if you see here, which of the following sorting algorithms provide the best time complexity in the worst case scenario, right? Quick sort doesn't provide best time complexity because it takes n square. Because I told you, right, partitioning, you don't know where it will partitioning. If it is sorted, then it will take n square. Bubble sort takes n square. Selection sort takes n square. Answer is merge sort, n log n. Right? That's something that we have covered. Which of the following is divide and conquer? Divide and conquer. Bubble sort is not. It's an iterative sort. Right? It's an iterative sort. We run 2 for loops. That's why it's iterative. This is also an iterative. We run 2 for loops. Heap sort is divide and conquer. Yes, heap sort is actually divide and conquer plus iterative. So there is a way to probably do heap sort in both the mechanisms. So if the answer has 2 answers, or it says that both answers are possible, then you can write heap plus merge. If it says only one answer is possible, then you will eliminate heap, because heap has both the ways to be done, and merge is the only way in which you can do divide and conquer. So that is, by the way, heap sort algorithm never comes, so I have not discussed the algorithm of heap sort, right? So but then if it comes again, please utilize your brains and just write some English statements as steps. I'm sure it will be easier in an iterative manner for you to probably do it. Prove that the best case time complexity for quick sort we have already done. Quick sort we have proven that it is n log n. We had taken in quick sort the divisions, and then we said that if it divides in the middle, then we will have log n levels, and each level we are doing n times of work. So n log n is the answer. We have proven that. The time complexity of heap sort in the worst case scenario, the time complexity of heap sort is also n log n, right? At each layer of complexity, the time complexity of worst case of heap sort is n log n. because it doesn't matter, because heap sort always starts from a max heap or a min heap. So how will the positioning of the elements matter? It doesn't matter. Write a quick sort algorithm to sort a list. Explain quick sort algorithm to sort a list. I have written the algorithm for you in C. I told you to convert it into English and explain with an example. So when you are explaining with an example, right, so please explain that. Let us say that you start with an array like this: 7, 15, 29, 5, 10, let's say 9. So let us say you start with an array. So you will say that the example will say that 7 is my pivot element, and after 7 is sorted, then the element will look like this, where I will have 7 as my 7 will be in the correct position. That means 7 will be here, and to the left of 7 will be your whoever it is. I mean 5 will be there, and only 5 will be there, and to the right of this you will have 15, 29, 5. It may not be in the proper sequence. Unless you do the example, the sequence will not come out, but they have asked only for an example. So you will probably give it like this: 15, 29, 10 and 9. All of this are greater than 7, and all of this are less than 7. So that's what you will try to achieve. And this 5 is already sorted, and we have reached the final state here because there is only one element, right? And for this, again, you will say that I will start with this, and therefore my array will look like 5, then 7, and then I will position my pivot here, and this 15 will come to the right position, and the left element will be less than that, which means 10 and 9 will be left, and my right side will be 29. So this is your next example, and then you will again say that my 5 is anyway single element, so it is done. 29 is single element, so it is done. Now between 10 and 9 you will select 10 as the pivot and try to position it, right? So you will position 5, 7, then you have 10 and 9 will be positioned, so 10 will be positioned in the proper place, and 9 will come to the left of 10, and then you will have your the rest of the elements, which is 15 and 29. So what did you do? Your pivot is now 10, and the other pivots that you had found out was the rest of the elements, right? So all the elements are getting covered. So all the elements are covered here. So you decide on how better you can probably write it, because you might not have these colorful stencils with you. So with pencil and pen, probably you can manage this for an example. Don't spend time on this example. Don't spend time to solve this example, because you are only supposed to write this algorithm, and you will explain it with an example by saying that in these iterations, every iteration will make sure that the pivot is in the correct position. Explain what is an ideal sorting algorithm. An ideal sorting algorithm. What do you want from a sorting? Small time, of course. Small space, yes. Stable, yes. Adaptive. That means if it is sorted, then it will be faster, right? That's what you want. Adaptive. So it understands, "Arey, ye to sorted hai, so I will complete it faster." Simple to implement, of course, and predictable worst case performance, right? So worst case, it should not say that I don't know what is the worst case performance. It should be predictable. One of the complexity classes should be there. So that is what is ideal sorting algorithm. Classify sorting algorithm based on parameters of stability, number of. This is what we have already established in that table, and I told you this question has come. This is the question. Next, write algorithm for bubble sorting. This has suddenly come up in 2017. After that, I have not seen your last semester algorithms, but if you remember bubble sort, there should be 2 loops, right? So one loop here, one loop here, iterative method. This loop will run till n-2, because in bubble sort you are comparing you're starting from 0, that means 0 to n-1, but 0 to n-1 will not satisfy bubble sort, because bubble sort compares I with a of I plus 1. So if you do n-1, then this I plus 1 will cross the bounds of the array. So remember that the second loop has to have n-2. The remaining, I think you can probably remember and recollect. Write merge sort algorithm, we have done. Pseudocode of merge sort algorithm, same thing. Implement merge sort in C code. This is the C code that they have given. After the algorithm, they are saying write it in C code. So they want the algorithm, then they want the C code. This is another year question. I have put it here, not the same question. Explain with a suitable example the principle of quicksort. I told you, right, quicksort, they might ask you what are the steps. So it is a divide and conquer. You will need to select a pivot. You will need to partition so that smaller items are placed to the left, greater items are placed to the right. That is what I have discussed time and again, and then recursively solve it. So you know the process, explain it in point wise. In which case does quicksort become a slow sort? You know that if it is sorted, then it becomes a slow sort because it becomes order of n square. Discuss remedies. Remedies are take a random element as pivot. Instead of taking the leftmost element as pivot, take a random element as pivot. Then there are chances that you can get a left and right subarray. And when you get that, you are dividing it, it becomes n log n. Compare the performance and operation of bubble sort, selection sort. You can check the table, it will have that. Is not a stable sorting algorithm, it depends on the choice given. Here we can write so many things. We can write selection, we can write heap, we can write quick. Right? They are not stable sort. Time complexity of bubble sort in best case is going to be order of n, because it will, best case means it is sorted, so it will be skipping the rest of the iterations. After the first pass, it will exit. When is a sorting technique called stable? We have discussed that many times. What will be the time complexity of selection sort to sort an array of n elements? Selection sort of n elements will always take order of n square. Merge sort uses divide and conquer strategy. Right, so that is there, and this is the last set of questions. Deduce average time complexity, we have done it. Define sorting. Sorting is what? Arranging elements in ascending or descending order. That's all. That is definition of sorting. Stable sorting we know. In place sorting we know. If existing array is sorted, you want to insert a new element without disrupting sortedness. What technique would you use? We have already discussed that, insertion sort. If the existing array is sorted and I want to insert one element, of course the easiest way to position it in the correct position, which is nothing but insertion sort. Why? Because insertion sort is adaptive. It effectively inserts the new element. Whatever I have explained, the same thing is written here. You are only shifting the element, you are not iterating. Right? So that is all that we had to cover from a sorting perspective. It is exactly one. We have completed our marathon, and we have also completed our DSA playlist, which is available in YouTube. This will be available as a lecture for sorting, and the lectures for hashing and graph we will pick it up from the marathon. I will place that same video in the playlist so that you can have a view of that also. So that being said, I don't have anything else unless you position any questions on the chat window. If there are no questions, I'll wait for 30 seconds. If there are no questions, then feel free to bounce anything that you feel from an examination perspective I need to answer on the common channel. The marathon channel will now cease to exist. If you want to be migrated to the talents batch and you are not part of the talents batch, I will position the WhatsApp link in the marathon channel so that you can position yourself into the talents batch, which we will continue till your 4th year. So that's in a nutshell what I wanted to convey. I hope the series of videos in YouTube that I have posted, it took a lot of effort for me to do that amidst all the things that I had to do. I hope that is useful for you. I hope you are looking at it. Please use it to the best of your abilities. If there are better videos, use that. I don't mind that. But at the end of the day, the knowledge should be there. The exams are near. All the best for your examinations, and please utilize my help whenever you need it through a WhatsApp ping. I am always a WhatsApp ping away for you. Chalo, have a nice weekend, whatever is left of it, and we will see you in college. Thank you.